Greetings, ladies and gents, and welcome back to Chapter 8 and Angular Motion, or what we commonly call rotation. Whoops. In any case, we're going to begin our study of angular motion or rotation, circular motion, whatever you want to call it, with a definition of a circle and its anatomy. And we all probably have some idea of what a circle is, and pardon me, I didn't major in art. I'm terrible at this kind of thing, but we all probably understand what the actual definition of a circle is, right? If you have some central point to a circle, all of the points on the circle are equidistant from that point. Or another way of saying that, and the way that it's usually stated, is that a circle is the locus of points equidistant from a reference point. Now, what that's really saying is that the distance between any point on the circle and the center are fixed, and this fixed distance is this funny thing that we call the radius, right? If you took one point on the circle and you drew a line from it through the middle to a line on the other side, we call this distance the diameter. And the distance all the way around the circle, we call that the circumference, right? Okay, that's all just the warm-up, of course. Next, what is the definition of the circumference other than it's the distance all the way around? Well, the distance all the way around the circle, the circumference, is related to the radius by this factor, 2 pi times the radius. That's probably pretty standard stuff. Most of you are probably already familiar with that. Now, what you may or may not know is that if we take a circle, let's say here's our center point, right? Here's our radius. Now let's say that we wanted to take a slice out of it, like a slice of pizza, right? Like so. The distance across the edge here, we call this an arc, and the length of this arc we'll label with the letter S. Okay? The angle that encloses, we'll call this theta. Okay? And now there's a relationship in between the arc length and the angle and the radius, and that is the arc length is equal to the radius times the angle. If you stop to think about it for a second, consider what this arc length is going to be if this angle is the entire circle. Well, if the angle is the entire circle, then the arc length is the entire distance around the circle, or the circumference, right? That means the entire angle enclosed by a circle is 2 pi. We call this kind of angular measurement radians, because it is akin to the measurement of the radius. Now, 2 pi is just a number, and I know a lot of times we usually say that the angle enclosed by a circle is 360 degrees. But these are actually saying the same thing. 2 pi radians is actually 360 degrees. Now this is a little funny to think, because 360 degrees, this degree symbol here, actually makes it a unit of measurement. But 2 pi is just a number, right? Radians is actually a unitless quantity. Now before we proceed any further, we have to define the concept of angular velocity, and that is basically how quickly something rotates. Linear velocity we defined as your velocity was the distance you traveled divided by the time elapsed. So like if you started here and you ended up here, this would be your distance, and then if you know the time that it took to get from there to there, you could solve for your velocity, right? Now if we're moving in a circle, it's slightly different. If we're moving in a circle, we move with some amount of what we call angular velocity. Angular velocity is typically represented by a lowercase omega. That is not a W, okay? That is a lowercase omega from Greek. And angular speed or angular velocity is slightly different from linear velocity. And that should become very apparent and obvious to you when I tell you what the units are. Common unit for angular velocity, colloquially is something like RPM, or revolutions per minute. But usually, we don't use that. We use radians per second. And if you were paying attention to what I said earlier, remember radians is not actually a unit. So we've just got 1 per second. This is the actual unit for angular velocity. Well, what does it represent? Well, consider, if you will, a rotating platform, like you have a DVD that you put into your PlayStation or your Xbox or whatever, right? DVD player. Now let's say that you have an object out here on the far edge, right? Or there's a little mark on it or something along those lines, right? And there's another mark here. Which one of these is going to move faster? Well, they're both on the same disk, right? And so they're both going to rotate through the same angle per unit time. And that's what angular velocity is. So because everything on this line, and everything on this line, everything on this line, this whole disk is going to move together, it's all going to have one angular velocity, right? It's rotating through a certain angle per unit time. However, if you wanted to talk about the actual distance that, say, this object travels, the one here at the edge, obviously it's going to go all the way around the Blu-ray, right? Whereas the one closer to the center here is only going to make this small circle. And because it's rotating together, obviously they're going to travel their respective distances in the same amount of time. And so an object here at the edge of the disk is going to have a greater, what we call tangential, like a linear velocity, right? Its velocity at any instant in time is going to be greater than the velocity of something closer to the center of this rotating object. Thus, we usually say that your tangential velocity depends obviously on how fast the thing is rotating, right? Your angular velocity. But it also depends on how far you are from the center, from the axis of rotation, right? So this object's radius, or the radius of its circle, is much smaller than the entire Blu-ray, right? Now, what should the units of tangential velocity be? Okay, well, obviously for omega, for our angular velocity, we've got 1 per second. And then distance obviously is going to be meters, so this is going to give us meters per second, which is what we would expect for a linear velocity, right? Now, if you recall from earlier chapters, if you're moving in a circle, like if you're driving a car, right? If you're traveling in a circle, what direction are you constantly accelerating toward? Well, you're not accelerating tangentially forward, that would just increase your speed, right? You're not accelerating tangentially backward, that would just decrease your speed. You have to be accelerating towards the center, right? Constantly changing your direction towards the middle. And if you don't believe me, imagine, of course, your car here headed this way. You have to turn your wheel to the left in order to make sure that you keep going in a circle, right? Pretty straightforward stuff, really, when you stop to think about it. Now, it just so happens that this center-seeking acceleration, what we call centripetal acceleration, for something to continue on with a constant linear velocity while moving in a circle, has to be related to its velocity, obviously, and also the radius. So we say centripetal acceleration for something that is neither speeding up nor slowing down is v squared over r. Whatever your linear velocity v is, divided by the radius or distance from the axis of rotation. However, it is possible, of course, to experience tangential acceleration, like if you hit the gas while you're driving your car and turning to the left, right? Now, I had planned on showing you a demo, but unfortunately that's sort of impossible given the current conditions. And so I've left a link to a demonstration video of why it is that trains stay on tracks when they curve, when they make turns, right, when they bank. So please take the time to go ahead and pause and view it now. And once we're done, we can continue. So if you take a styrofoam cup or something like that, and you just roll it on the ground, it's going to roll in a circle. Why? Well, styrofoam cups are usually shaped something like this, right? And they have a smaller radius at the bottom and a larger radius at the top. And so when this rolls, this one is going to make a wider circle than this part, right? And that's why they roll in a circle. It's pretty straightforward, really, when you think about it. And that's very much the same reason why trains always stay on tracks. Obviously, the entire train wheel is going to roll together, just like the entire styrofoam cup is going to roll together, right? Now, obviously, the larger radius, the rim of the cup, for example, is going to have a greater tangential velocity, right? It's going to cover a greater distance, greater linear distance, in an equal amount of time. And since this part, therefore, is literally moving faster, this is going to move in a circle. And that's why the wheels on a train keep it on the rails, right? As soon as it starts to slide up, it'll move to a place that's wider on the wheel, and so it'll rotate back inward. But you already saw that in the video. So like a train, the slanted wheels move the train back towards the middle when it gets away from the center, because the wider part of the wheels move faster. Now, if I take, and I don't have a meter stick like I indicated in my class notes, but if I took a ruler or something like this, and I shoved it on the end, it's going to accelerate, right? However, if I push it on the end, it rotates instead, right? Now, not everything is as easy to rotate as everything else with the same mass. If you take a barbell and try to spin it, you might be able to do it. But it's harder if you move the weights farther away from the handle, right? Why is that? Well, that means the mass is at a greater distance, a greater radius from the axis of rotation, right, where you're trying to rotate it from. Thus, the object's what we call moment of inertia, which the book calls rotational inertia, and no physicist ever has ever used that terminology. But the object's moment of inertia, therefore, depends not only upon its mass, but also the distribution of the mass, especially relative to the axis of rotation. So let's say that you wanted to take a meter stick. And now this is not quite a meter stick, but you get the idea. So let's say that you took a meter stick, okay, and it has all the various markings on it, right? And you wanted to take this meter stick and rotate it about this end, right, so that this end swings out. It's going to have to make this huge arc, and as a result, its moment of inertia is 1/3 the mass of the meter stick times the length of the meter stick squared. But this is about the end. But if you wanted to rotate the meter stick about the center, right, and just kind of rotate it so that end swings that way, that end swings that way, you can see that the arc that it swings in isn't nearly as big, right? Around one end, this makes a 1 meter radius circle, and this is only half a meter. And so about the center, the moment of inertia is much less, 1/12 times the mass times the square of the length. Long story short, it is 4 times more difficult to rotate a meter stick about its end than it is to rotate it about the middle, because the mass is distributed differently relative to the axis of rotation. Interesting, right? Now, just in case you need this, especially for, homework questions or whatever, the moment of inertia for a point mass, like a single dot of mass, is the mass times the radius squared, or the radius is like the distance of the point mass from the center of from its axis of rotation, right? The distance that it's moving around. Now, I want to pose a question to all of you. Let's say you have 2 objects. One of these objects is a disk, and it's solid, right? It's got a uniform mass distribution, right? It's got as much mass here and here and here, and the whole way through it's basically got the same consistency. But then you've also got, sorry, I'm terrible at this. You've also got an object, and let's pretend that I didn't draw this so terribly, but that they both have the same radius, they're the same size, right? But this one is hollow, right? It's just a ring. All of the mass is at the end. Now, if you took both of these objects, this disk and this ring, right? Let's say that they have the same mass, they're the same size. Just this one has all of its mass at the edge, and this one has an even mass distribution. Now let's say you took both of these and you rolled them down the same ramp. Which one would get to the bottom first? It's an interesting question, right? And unfortunately, I'm not able to do this demonstration either, but I've also left a link on today's lecture page, as well as in the class notes. So go ahead and have a look, pause your instructional video, and go ahead and watch that one now. Now, why was it that the solid object rolled faster? Well, it has a lower moment of inertia. Why? Well, it has some mass here, some mass here, some mass here, and so all of this mass is more evenly distributed, whereas the mass here is all just right at the radius, right? Each individual chunk of mass is at the maximum distance, and so its moment of inertia is much higher. Rotating it takes, the solid object will roll faster because it has a lower moment of inertia, and rotating it takes less of its potential energy, right? And so more of that potential energy can go into making it translate, roll faster. So objects moving in smaller circles require less energy to move than objects moving in great, huge circles. Makes sense, right? Now, if you want something to rotate, the moment of inertia is what resists the rotation, very much in the same way that mass is what resists acceleration. And also in very much the same way, if you want to apply a force to something, you can make it accelerate, but you have to apply a torque to something to make it rotate. Like pushing the end of a ruler like so tangentially, not through the center of mass, tangentially. Just like using a lever, or like a crowbar, right? The greater the distance from the point or to the point of rotation, usually the center of mass, the greater the torque. Also, the more force you apply to a crowbar, obviously the more torque you're going to get out of it. And so the torque really is a combination of factors. We usually write that this way. Now this is not a T, this is the Greek letter tau. And let me try to use the broad side of the pen so it'll show up a little better. Okay, so tau, or torque, we say is force times lever arm. Actually, we usually write it lever arms with the cross product of force, but let's not worry about that. Suffice to say, the longer the lever arm is, the more torque you're going to get out of it, which is why you use a big long crowbar and only stick the very end in whatever you need to pry open, right? But also, the harder you pull, the greater a force you apply, the more torque you're going to get out of it, right? Long story short, torques are what cause things to rotate. And you can only do that by applying a force at some lever arm distance from the center of rotation, right? Obviously, you can't apply it directly to the center of mass of an object, otherwise it's just going to make it accelerate instead of rotate. Okay. Now, for an object not to rotate, or not to change its rotational condition, right, what we call rotational equilibrium, and I hope this one is obvious, that the sum, obviously this is the Greek letter sigma, it means the sum or the summation if you add up everything together, right? And if you added up all the torques on an object, they have to be 0 for an object to remain at rotational equilibrium. Obviously, I'm not applying any torques to this object, right? But if I were to apply a torque, a net torque, it would cause it to rotate. And at that point, the sum of all torques would not be 0. So consider, if you will, two kids sitting on a seesaw. Here's the pivot point in the middle, right, that the seesaw is going to balance on. Here's our board. Okay, so if one kid sits here, 1 meter from the center, where should another kid that has double that mass sit in order for this system to remain at rotational equilibrium? Well, we said that torque is force times lever arm, right? What force is being applied here? Well, obviously we're talking about the weight of the kid, that's mass times gravity, right? Okay, so the torque on this side is going to be mg times 1 meter. So obviously that's just mg, right? Now, call this r prime. Now, it's not fair to say that you have positive torques or negative torques. It's fair to say that you have maybe clockwise torques and counterclockwise torques. So this one is going to be a clockwise torque, right? And we want to have a counterclockwise torque that's equal to this torque, right? So we want our counterclockwise torque to equal mg. Okay, now what do we got here? This other torque is going to be our distance, what we call r prime, times the force applied here. But we already said that this kid has twice the mass, right? So this weight is going to be 2mg, right? So we got r prime times 2mg, but this has to equal mg. Well, how could this possibly be? Well, let's balance the equation. R prime times mg is equal to mg over 2. Let's cancel the mg's. So then that means r prime is 1/2 a meter. Long story short, if we get double the weight, we have to put it half as far away in order to get the same torque. Okay, makes sense? Obviously, if this doesn't make any sense, please email me. Come to office hours, whatever you need to do. Now, moving on, the book calls the center of mass by another name, the center of gravity. And let me reassure you that we don't use that term. It is true that the object moves as though the force of gravity is applied to it at the object's center of mass, and so the book kind of uses this funny terminology, but I think the author invented that one, because nobody ever says that. Long story short, the center of mass is the geometric center of all the mass in an object. And what I mean by that is, let's say you have a rock or something, right? Okay, so you got a rock. And let's say you've got your reference point here. Now, you wanted to take some chunk of mass here, and you wanted to measure the distance to that chunk of mass. We'll call that r sub I. We'll call this mass r sub I, right, for the ith mass. I is just a dummy index, don't worry about it. It'll make sense here in a second. Now you would say the center of mass is if you summed up the distance or the mass, some little chunk of mass here, and you multiplied it, by its distance from this reference point, and then you also divided by the distance to this reference point, right? You would figure out where the center of mass is. Now what this is saying is, let's look at chunk I, right? It has a certain amount of mass, it's a certain distance, okay? And then we're going to divide by this distance to figure out what the average is. So we're going to take another chunk, figure out how massive it is, see how far it is from this reference point. We're going to take another chunk, figure out how massive it is, figure out its distance to the reference point. We're going to add up all of the little mass chunks in this whole object. And then we're going to divide by each of their distances to figure out where the average, where the geometric mass center of this object is. That's what a center of mass is. And that's why it has this kind of strange notation. That's what it means. Okay, if I take this meter stick and I throw it, it'll look like it's tumbling end over end, right? But it's actually tumbling about its center of mass. And when you see it spinning, there's a point in the middle that kind of looks like it's the rest of the ruler is rotating about it, right? Now, if I took this object and I was out in space and I threw it, it would just tumble about this point forever, right? It just keep flipping and flipping and flipping and flipping over this spot in the middle that appears to be immovable. If I throw this object into the air, then that non-moving point looks like it's moving in a parabolic arc, just like, you know, if you take anything else and throw it, it moves in a parabolic arc, right? Like if you throw a ball or whatever. Now, if I wanted to try to balance this meter stick, if I wanted to figure out where the center of mass of this meter stick is, you just move it, you balance it on its edge here until it just barely starts to fall. That's not it. That's not it. That's not it. Oh, there it was. What do you know? Right about at the 6-inch mark. I don't know how well you can see that. But right in the middle, right where it's supposed to be. Okay, if I tie a string to an object and swing it around, as long as I'm holding on to the same point on the string, or the cable, or what have you, what kind of motion is it going to make? Well, obviously the length then is fixed, right? So the distance from here, this object is going to be moving around in a circle, right? Apologize, I didn't really show up so well. There we go, that's a little better. So this object is going to move in a circle, right? Because the length of the string is fixed, it's a radius. Now, what direction is it constantly accelerating toward? We said that earlier. It's got to be accelerating towards the center, right? And if it's moving with constant speed, it's moving with a constant centripetal acceleration, right? You guys remember that? Our centripetal acceleration is v squared over r. Now, let's say that this object that we're swinging around has a certain finite amount of mass. Like if I were to take the end of my earbuds and swing it around in a circle, right? This has a certain amount of mass. And then if I'm holding it here, it has a fixed radius, right? So if I hold it here and I swing it, I have to apply a certain amount of force to it, right, in order to make it constantly move like so. Move with a constant velocity in a circle. So if I'm going to give it the centripetal acceleration, I have to apply a force to it, a centripetal force. And obviously, according to Newton's second law, right, force equals mass times acceleration, that means the centripetal force that you have to apply to an object to make it move in a circle with a constant velocity is its mass times its centripetal acceleration, v squared over r. Now the centrifugal force is not to be confused, or centripetal force, excuse me, is not to be confused with the misnomer, the fictitious force, this thing that doesn't actually exist called centrifugal force, which is what an astronaut experiences when in a centrifuge. Centrifugal force does not actually exist. It is mathematical fiction, and so we call it a fictitious force. And the reason for that is actually pretty simple. If I swing something around in a circle and I let go, what's going to happen? It's going to want to move in a straight line, right? And if you remember Newton's first law, objects in motion want to remain in motion, right? So if you're a car driving around in a circle, the car is going to want to go forward unless you continue to turn the wheel, right? If you just let the wheel go, the car is just going to go straight. Things have inertia. In the real world, things like to move in straight lines, unless acted upon by some kind of net external force, right? And so, if you're an astronaut in a centrifuge, you want to move straight forward, but the walls of the centrifuge pod that you're in are going to make you move around in a circle. And so, it's going to feel like it's pushing you, but really you're pushing outward on the wall if you're this astronaut in training, because you want to move in a straight line. Now, for most of us who maybe don't feel so strongly about trying to become astronauts, just don't turn your steering wheel too sharply as you're driving fast, or you may slam into the door, or at least lean, and if you're turning the other way, you lean towards the center console. We have theorized for some time that we could maybe use rotating pods on a space station or a spaceship or something that would rotate and therefore simulate gravity. But unfortunately, we have not yet been so successful with that. That's going to take a whole lot of doing. In any case, recall that momentum in the linear sense is mass times velocity. And usually, we use a lowercase p for that, right? Momentum is mass times velocity. Now, obviously, if something is rotating, you're going to have to apply a certain amount of force over time, right? A certain amount of torque over a certain amount of time in order to try to reduce its momentum to make it stop. Thus, objects also have to have angular or rotational momentum as well. Now, of course, this doesn't just depend on the mass, as you might expect, but it depends more directly on this funny thing that we call the moment of inertia, right? It also, of course, depends upon how fast you're moving, what your angular velocity is. Now, for a point mass, of course, for a single mass body, the moment of inertia, we said, was mr squared. And strictly speaking, omega is your velocity divided by the radius, or the distance from your axis of rotation. And so generally we write it this way, mv_r. Because your angular momentum depends upon your mass, your velocity, and your radius, or your distance from your axis of rotation. Therefore, the rotational analog of Newton's second law you can sort of write this way, right? Is that an object will remain at constant rate unless acted upon by a net external torque. Recall that conservation of angular momentum was one of our conservation laws, right? Conservation of momentum. Well, angular momentum has to be part of that, doesn't it? Thus, if you were standing on a turntable and you're rotating with your arms out, just like the figure skater who begins their, what do you call it, a toe loop, with their arms and their legs out, and as they pull their limbs inward, decrease their radius, their velocity has to increase because your angular momentum has to be conserved. So your angular velocity has to increase as your moment of inertia decreases, right? When you pull your arms in, you spin faster. If you don't remember, go ahead and have another look at the turntable demo video, both in the lecture notes and on the lecture page. In any case, I hope you've enjoyed today's lecture. I'll see you again soon for Chapter 9.